Hello, my name is Doug Bowman from Virginia Tech, and I'm here to present the work Spatial Bar, Exploring Window Switching Techniques for Large Virtual Displays. This project was led by my former PhD student, Leonardo Pavanatto, and we also collaborated with Jens Grubert. So the motivation for this work is that many current XR systems, such as the Apple Vision Pro, can provide large virtual displays. That is, desktop computer-like displays that are viewed through an XR headset. And of course, because they are virtual, they can be very large and flexible, used anywhere. And in particular, these large displays can contain many windows, and we know from prior work that this has the potential to enhance productivity. But there's also a cost to using such large displays, and in particular, we're interested in window management overhead. So users of these virtual displays have to do quite a bit of work to arrange windows on the display, to find windows that might be hidden, to focus windows that are not the current focus, even to find the cursor, and of course, lots of effort to move the cursor using a mouse or trackpad to different locations on the display. So existing tools for window management, and in particular for window switching, like Alt-Tab or Taskbar on Windows machines, or the Dock or Expose on Macs, are really not designed for or ideal for large displays. They still require lots of visual search, lots of key presses, or lots of cursor movement. So our question was, how do we improve window management on large virtual displays? So there are two key elements of our approach. First, we make use of underutilized spaces. That is, space that is not used by the display, but could be used for smaller interfaces. And so these are spaces like the space underneath the display, between that and the keyboard, the space behind the display, or even space attached to the user's body. Secondly, we believe that we can take advantage of additional sensors in XR headsets, such as eye tracking, to provide different sorts of input modalities. And so in particular, we use this gaze and click approach, where you combine eye tracking for pointing with a separate selection confirmation using the primary input device, your mouse or trackpad. And so a question here is, if you are transitioning often between using the mouse and using eye tracking, how do we facilitate that transition between modalities for users? So our approach, our technique is called Spatial Bar, and Spatial Bar is similar to a taskbar or dock. It's positioned, however, below the computer display in one of these underutilized spaces. It displays thumbnails of all the open windows in the system, and those thumbnails are organized into categories. So there's two selections that need to be made to switch to a new window. You select a category, and then you select a thumbnail within that category. We use gaze plus click to make selections in the spatial bar. And after a selection is made, we provide an animation to help the user find the user on the large display. And we also can teleport the cursor to the center of that new window to facilitate the switch between modalities so that it's easier for the user to know where the cursor will be and to begin using it again. So we ran a study to help us understand the effects of input modality and cursor behavior on performance, workload, and user experience during window switching on large virtual displays. We had 16 participants, and we varied primarily the method of selection, that is gaze versus cursor, and the teleportation behavior, whether the cursor teleported after window selection or whether it stayed in place. We also varied the distance between both the previous window and the spatial bar, how far you would have to move to get to the spatial bar, and the distance between the spatial bar and the next window in two different distances, short and large. We measured the time to select the thumbnail in the spatial bar, the time to select a button on the new window, and the total time. We measured errors, workload via an SFTLX, and also performed an interview and gave people a ratings questionnaire. So here are the conditions in our study. The first one is our proposed condition, which is gaze teleport. And in this condition, the user selects the window in the spatial bar with gaze plus click. The cursor is teleported to the location of the new window, and then the user uses the mouse cursor to select a next button to find out what the next window they're supposed to select is. Then we had the gaze stay technique where, again, you select in the spatial bar with gaze, but the cursor remains in its original position on the large display and has to be moved manually over to the new window. Then we have the cursor teleport condition. Here you move the cursor down into the spatial bar in order to select a thumbnail, but then the cursor is teleported to the center of the new window. And finally, we have the cursor stay condition, which is the traditional condition where you move the cursor manually down to the spatial bar, select the thumbnail, and then move it manually up to the new window to continue interacting. So we implemented this as a VR simulation. We had a curved 8K virtual monitor in Unity. We used VR to reduce distractions, so there's no real-world background and to control the environment. The headset was a MetaQuest Pro for head and eye tracking, and we used an Apple Magic trackpad as the input device. We chose not to use a mouse because the use of mouse clutching is highly variable between users, and we feel that a trackpad is a very common input device, especially for virtual displays that might be attached to laptops. Our task, as shown in the video, was just to switch between windows. So you start from a window on the large display, view the next target window, select that window in the spatial bar, and then click a Next Task button, which appeared randomly in the selected window, not at the center. So here are our objective findings. First of all, in terms of selecting the correct thumbnail in the spatial bar, we found that gaze was 17% faster than cursor when the distance was large. However, in the short distance trials, the cursor was actually 7% faster than gaze, and both of those differences were significant. In terms of user perception, participants believed that gaze was better for quickly selecting the desired thumbnail in the spatial bar. So overall, gaze was perceived as faster. Secondly, we found that for the selection of the button in the new target window, that teleport was always faster than stay. And it was 41% faster on large distance trials and 24% faster on short distance trials. In terms of user perception, again, participants perceived that teleport was faster, 33% higher score on that question. And as far as overall window switching, they also believed that gaze and teleport were faster, 20 and 21% higher on the score there. In terms of physical demand, we found that teleport provided lower physical demand, 49% less physical demand than stay, which is obviously because of the extra effort needed to move the cursor back up to the new window in the stay condition. None of the other workload measurements were significant. When we interviewed participants, they appreciated the cursor stay technique because it was familiar. It's just like how computers operate in their daily lives, but they found it laborious on the large display, especially at large distances. Gaze teleport was novel, but they also found it intuitive. And for large distances, they believed it was the fastest, and that the learning curve was not significant for gaze teleport. Cursor teleport, on the other hand, was sometimes confusing. So because you had to move the cursor manually to the spatial bar, but you did not have to move it manually to the new window, that felt inconsistent. And users often, as a result, overshot the button that they were trying to press. And then the gaze stay technique really required switching modalities in a way that people found mentally confusing. In addition, they had to remember the cursor location on the display before they selected in the spatial bar. So in conclusion, we found that spatial bar really can leverage underutilized space and gaze plus click that streamlines window switching as an important part of window management. And we believe this is really promising for large displays and could be applied to virtual display systems that are in use today. In the future, potential improvements in eye tracking will increase the reliability of gaze, and so this technique could be even better. Our study was somewhat limited because it was in VR and used a trackpad along with simplified tasks, and so we need to study real-world usage on real productivity tasks with more complicated window arrangements. Thank you for listening.